Okay. So we have identical containers, cross-sectional areas, A sub CS, and a delta Y difference between the water levels. We want to find the potential energy difference. First attempt was you multiply the cross-sectional area by delta Y, but that gives us the difference in the volumes, right? Okay, so how are we going to get the difference in the potential energies?
Oh, yeah.
So that would be
One half.
one half mv squared. Can we find kinetic energy and then transfer that or
Say it's
use
the
that.
opposite.
Equal and opposite? Can we get kinetic energy and say equal and opposite?
We eventually will, so you're thinking along.
1/2 mv squared.
Yeah, the whole idea of relating this to kinetic energy, and it's good that you're thinking of that. Okay, but that's not what we need to do to get the change in potential energy. Once we have the change in potential energy, that's how we're going to use it. Okay, so
Okay. So we just
good
get the
thinking,
same-
but how do we get the change or the difference in the potential energies?
That's like.
One other thing I should have specified and didn't. We would have maybe a 0 point for the potential energy at any point we wish, but I'll specify it right here. Okay? Well, what do we need? Why is there a difference in potential energy?
What's the water?
Because of the change in water.
Change in water.
Well, I mean, there's a difference in the water levels.
Okay. Why would that give us a difference in potential energies?
Because you,
More force pushes
Before
down
the-
on them. More force.
should go up in this.
Well, why is there potential energy here in the first place?
Gravity.
Because of gravity, because potential energy, a change in potential energy is equal and opposite to the work done by gravity, right? Okay? So, the level goes from here to here. Something is changing the potential energy relative to this, and that would be gravity, right? And it turns out that that's going to be equal to the work done by gravity if I take the chunk of water here that isn't here and lower it to here. Okay? So,
So that's why I'm minus whatever
Yeah, whatever.
that is, whatever that distance, so Y2 is.
Yeah, Y1, Y5. 4.
we take this chunk of water, right? And let's move it to here. Let's assume it's a thin chunk, a small delta Y. Okay? Then how much potential energy change is there related to moving the water from here to here?
Be the volume times its density, or
Yeah, the volume times the density
times gravity,
times the acceleration of gravity, exactly.
times distance.
Yeah, times the distance, right? Okay, so. Delta PE is the mass. Times G. Times what?
I guess distance or displacement.
What would that be?
Delta Y, right? The distance between the water.
It doesn't move from here to here, it moves from here to here. Why, right?
Oh, okay.
Okay? Now there's your MGH that you love so much, okay? Except that it's not Y, it's negative Y, right? Because you're moving from here to here. Okay? And I'll call this the layer of water. It's like you got a little layer of water here that's being replaced by water down here. Perhaps by exiting through a hole in the container. Okay? So, delta PE of the layer is this. Okay? Of course, we don't know what the mass of the layer is, but Lane has already mentioned what that would be. Right? And the mass is rho times your delta V.
Because density
Yeah.
is.
Okay?
Right.
Which is then rho times your cross-sectional area times your delta Y.